Okay, I want to do one more quick video for chapter 23 on electric potentials. Before you watch this video, make sure you've gone through the examples in chapter 23 yourself a couple of times so you can do those on your own, and then you can watch those videos where I go over those examples. Today I want to talk about the relationship between a scalar potential field and a vector field. And the relationship between a potential and a vector is really important or a potential in a field is really important in physics. And is one of the reasons that physics majors tend to take Calculus 3 is because that's when you learn about functions in three-dimensional space and vector operators like the gradient, the divergence, and the curl. So for those of you who have taken Calc 3, some of this will be familiar. For those of you who haven't, it'll be a good preview of those courses. I just went to Wolfram Alpha and picked a random function to graph, a function that is z is equal to sine of x squared plus sine y squared. So this is a function in three-dimensional Cartesian coordinates. The xy plane is down here, and the z coordinate is equal to the sine of the x coordinate plus the sine of the y coordinate squared. And what we see is a very complicated function in three dimensions with a bunch of peaks and valleys like you might expect with a sine-based curve with one big dip here in the middle and a bunch of peaks around that in both the x and y directions. Wolfram Alpha also produces this sort of top-down, you can almost think of it as a topographic map or like an altitude map. For example, this big dip in the center is this big circle right here, and then around that there are these 1, 2, 3, 4 peaks. Sorry, well, sometimes I point with my mouse and I think that it shows up on the screen, and it doesn't. I can see the little pointer, but you guys can't see the little pointer. So there's 1, 2, 3, 4 peaks around that, and that corresponds to these 1, 2, 3, 4 peaks around that. Then there are 4 deep valleys there, and there. Those correspond to these regions here, here, here. So if you've ever seen a topographic map or an altitude map, you can see that on this function, the Wolfram Alpha has drawn these lines of constant altitude. So we can look at each of these lines over here, say this line around the center, as being a line in this hole in the middle of constant altitude. And so this is a good way to visualize a two-dimensional function in three-dimensional space, just looking at a sort of altitude map of the z coordinate, which is a function of the x and y coordinates. The idea of a gradient is the gradient operator, which operates on a scalar function in space, and it gives you a vector valued function in space, is the gradient tells you at every point in a function. Well, actually, let's step back for a minute and think about what the slope tells you. When you draw a function and ask for the slope, what does the slope of a function tells you? It tells you, sorry, the derivative of a function. If you've got a function in two-dimensional space, just a xy Cartesian coordinates, I'll draw it down here. You've got some function f that is a function of x. And you take the derivative of that function. What does that tell you? It tells you the slope of that function at every point x along the horizontal axis. In 3 dimensions, or 4 dimensions, or 5 dimensions, or any number of dimensions, the idea of gradient is similar. For a scalar valued function, the gradient tells you at every point the slope in the direction that the function is the steepest. So if I pick this point in the function, I can go on I can go up, I can go down, I can go horizontally along the function, but there's one particular direction at every point where the function is the steepest, where if you were imagining this as a bunch of hills that you were standing on, the direction tells you, the gradient operator tells you what direction you would walk in order to be ascending the steepest direction on that surface. So this function, if we call this f of xy, is a scalar function. But the gradient, and we usually use this upside down triangle, of f of xy, is a vector that tells you in what direction is that function increasing the steepest and what is the slope in that direction. We've got Wolfram alpha at our disposal, so we can actually ask Wolfram alpha to graph, and here I have asked it to plot the gradient of the same function, sine of x squared plus sine of y squared, between those same limits, x and y equals 3. And we can see is what we get is a vector-valued function, an arrow at every point in space that tells you the slope of that function in the steepest direction. So for example, here in the center of the bowl here, in the very center, it's flat, and you see that the gradient here is 0. There's no arrows at all. As you go in any direction, there's little tiny arrows pointing up the hill, these 4 hills right here, and then when you get over that hump, okay, if we draw this little, okay, I don't even know what to call it, little space between those 2 hills, once you get to the other side, the arrows point up again, because once you get to the other side of that, the steepest direction of that function is up that hill. Here are places in the corners where there's a function pointing up a hill, up a hill, up a hill, up a hill, that correspond to these 1, 2, 3, 4 very sharp peaks in the corner of our image. So the gradient is a vector-valued function, or the gradient, if this is f, the gradient of f is a vector-valued function that tells you something about the direction in which that function is changing the greatest. What does that have to do with fields and potentials? If we think about a potential function in space, there's some electrical potential in space due to some charge distribution in space. We already saw that the relation between the potential in the field is that the electric field is equal to the gradient of the potential function, actually the negative gradient of the potential function. And if we imagine that this was a potential function, that this was some function v of xy that gave you the electrical potential at every point in space, the gradient of this function, or actually the negative gradient of this function, gives you the direction that the electric field vector would point in that space. So at the center of this, there is no gradient. The function is flat. The electric field is 0. As you go up these hills, out of that valley, the electric field is equal to the negative gradient. It points down the hill. You can think of it as the direction that a ball would roll on that hill is the direction of the negative gradient, the direction in the opposite direction of the steepest direction. So here, and these 2 peaks around the center, a ball would roll down, 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 down this way, and it would roll down, 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 and so on. Now, if we think about this image as being like an elevation map, where every line on this 2-dimensional function represents a line of constant altitude or constant elevation, if we think about this as like just a map of a bunch of hills. Hopefully it's clear that wherever you are on this map, the direction that a ball will roll is perpendicular to these lines of constant altitude, which for a potential are called equipotential lines or surfaces. If we're in 3 dimensions, these equipotentials are surfaces. So if you draw the equipotentials of a field, the field lines, which are given by the negative gradient of that potential, are always perpendicular to that field. What is the gradient operationally? How do you find the gradient of a function? If you're in Cartesian coordinates, the formula for finding the gradient of a scalar valued function is actually very simple. It's a vector that's equal to the partial derivative of the function in the I direction, partial with respect to x in the I direction, plus the partial derivative of the function with respect to y in the y direction, plus the partial derivative of the function with respect to z in the z direction. So this gives you a vector at every point in space, which is what we call a vector field. So taking the gradient of a scalar function gives you a vector function. And remember that the relationship between the electric field and the potential is that the electric field is equal to the negative gradient of the potential function. So I could give you some potential function in three-dimensional space, say v of x, y, and z is equal to 2x cosine y e to the z. And you could use this formula to take the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, and find that electric field. Let's do it. Okay. The electric field that corresponds to this potential would be E equals negative the derivative of this function with respect to x, which is 2 cosine y e to the z in the x direction, plus the partial derivative with respect to y, which is 2x sine y, actually minus sine y. Oh, well, we've got a minus out front of the whole thing, so the minus actually makes that a plus. Minus e to the z in the y direction, which we usually write as the j hat unit vector, minus 2x cosine y e to the z in the k or the z hat direction. And that's a three-dimensional vector field that would tell you, given this electrical potential in three-dimensional space, what is the electric field vector at any point in space x, y, and z, and what directions does it point. That's not something we'll do in this class. We won't be actually computing three-dimensional vector fields from potentials, but it's something you'll be doing in a, say, sophomore level electromagnetism class if you ever get to that point in your physics studies. It's worth noting that the expression for the gradient and how you take the gradient is much more complicated in cylindrical coordinates and spherical coordinates, just like the expressions for, I don't know why I keep doing that, the expressions for the differential elements of volume are much more complicated in cylindrical and spherical coordinates than just dx, dy, dz. The expression for the gradient operator, this thing that you have to do to the scalar function to get the vector function, is actually way more complicated. We won't deal with that. Again, that's something more for an advanced undergraduate electromagnetism course. What we do want to be able to do in this course is to be able to, given a equipotential field, in other words, given a drawing of the potential in space where every one of these dotted lines represents a surface on which the potential is equal, to be able to draw the electric field from that potential. So we think of these equipotential surfaces as a topographical map. So this is a hill. This is the, sorry, again, you can't see my mouse when I don't have the pen on. This is the top of the hill, and this is going downhill, downhill, downhill. Okay? And every one of these dotted lines represents a line of constant altitude on the hill. So imagine this hill was covered in grass and you were mowing the grass. If you stood here on the hill, the direction you would want to walk so that you were going neither uphill nor downhill is along one of these lines of constant altitude or constant elevation. So if I was to, let me delete all these little arrows, say this is your equipotential surface, what is the direction of the electric field, or sketch the electric field due to this equipotential surface, how would I do it? Well, remember, if this is increasingly negative potential, the gradient of this function is uphill, but the field is given by the negative gradient, the direction that a ball would roll on this imaginary hill. So, oops, I went one too far. If I was here on the hill, I would roll downhill this way. If I was here, I would roll downhill this way. If I was here, I would roll downhill this way. If I was here, I would roll downhill this way. Notice the field lines are always perpendicular to each equipotential surface. As I get further and further down this hill, notice the equipotentials get further and further apart, meaning that the hill is less and less steep. Where the lines are close together, the lines of constant altitude are close together, like here, that is where the function is changing rapidly. The steepness of the hill is changing fast at that point. So here my field vectors would be big because the change in the steepness is large at this point on the hill. Here, field lines would be big. There's a large field at this point because the field is changing steepness quickly, and those lines would get shorter and shorter as we go to the less and less. Here it would be very, oops, make that even shorter than that. Here the lines would be very short because the field is very shallow there. So drawing the field then just becomes a matter of drawing perpendiculars to the equipotential that are large when the equipotentials are close together and smaller when the equipotentials are further apart. And so from this equipotential surface, I can sketch a field everywhere in three-dimensional space. And if I were to, say, just delete that equipotential, can I do that? Okay, I would leave behind a picture of the electric field due to that equipotential surface. I should also be able to go the other way around. I should also be able to, say I was given a field in space. Let me draw just some arrows. Arrows, arrows, arrows. Okay. Suppose there was something creating an electric field like this in space. What would the equipotentials of this field look like? Well, the equipotential surface everywhere is going to be perpendicular to the field lines. So the equipotential surfaces would be something like this, and they would be connected to places where the lines are about the same distance apart. So something like that. Okay, that's not very perpendicular. That. Okay, so the equipotential surface here would look something like this. This is really hard to draw with this tablet, but you'll get the idea here. Okay, perpendicular, 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 something like that. Here, okay, perpendicular, perpendicular, something like that. Here, perpendicular, 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 something like that. Here, perpendicular, something like this. So once you play with the idea of equipotentials for a while, you should be able to develop a feel for this relationship between the field lines and the equipotential surfaces that correspond to those field lines. Let me really quickly, before we stop today, take a look at the lab activity that I want you guys to do next, which is using this this app that lets you place electric charges in space and to sketch the electric field. I'm just going to make a little electric quadrupole here. Okay, so here's sort of two dipole fields superimposed on one another. We can see the direction of the field vectors. This is what we did in our last activity, just to get used to kind of getting a feel for the electric fields of different arrangements of charge. This little tool over here that you can grab it and pull it out of the window is a tool that lets you measure the potential at. So it's a little, think of it as a little potential measuring meter. Notice that as I move it around, the number changes to show you the potential. So for example, if I get close to the positive charge, there's a very big potential, 76 volts. As I get further and further away, 17 volts, 7 volts, 2 volts, okay, 0.5 volts. If I get very, very close to a negative charge, there's a very big negative potential, negative 37 volts, negative 18, negative 9, and so on. If I got right to the very center of this, okay, I should be able to get almost zero potential because there's an equal pull and an equal contribution to the positive and negative potential due to all four of these positive and negative charges. But the other thing this lets you do is, suppose I pick the potential here, get it to be about negative 5 volts. If I click on this little pencil, it draws an equipotential surface corresponding to that 5 volt potential. If I go to negative, let's try to get negative 3 volts, find a place in space where it's negative. Well, let's do negative 2 since I'm already there. Click on the pencil, I get a equipotential surface corresponding to negative 2 volts, about negative 1, okay, negative 0.5. And I can do that. Now let's find one that's about positive 10, and then about positive 5, and then about positive 2. I'm just doing this really, really quickly to demonstrate how it works. And then positive 1, and then positive 0.5. I'm going to get pretty far. Notice the further I get, the slower these potentials change. Notice that equipotential actually wrapped around to the other side. Bring my tool over here. I can fill in this space. And as I go around in the space creating equipotential surfaces, I can start to get a feel for the shape of this potential function in, well, I was going to say three-dimensional space, but this is just a two-dimensional slice of that space. So what I've got here is a bunch of equipotential surfaces that correspond to the electric field. Notice where the electric field is weak, say out here, the equipotentials are far apart. Why? Because the rate of change of the potential from one place to another is small. The steepness of the change of that potential, or the gradient of that potential, is small. Here, where the fields are strong, they're also changing quickly. The steepness of the rate of change from one potential to the next potential is very, very high. So where the field is strong, the equipotentials are close together. Where the field is weak, the equipotentials are further apart. And also notice that the arrows that constitute, or that stand in for, or we use to represent the electric field, are always perpendicular to these equipotential surfaces, at least to the accuracy that this program is able to draw those little arrows and make them visible to us. If we shrunk them down infinitesimally small, they would always be exactly perpendicular to these equipotential surfaces. So what you'll be asked to do in the lab activity, which I'll probably post on Thursday or Friday and give you a week to do it, is to, for various arrangements of electrical charge, to predict the shape of the equipotential surfaces of that arrangement of charge based on your intuition for what will be the shape of those field lines in three-dimensional space. Playing with this for a while, even doing some arrangements of charge that I don't ask you to do in the lab, is really, really, really useful as far as giving you an intuitive feel for the shapes of electric fields and the shapes of equipotential surfaces around different charge distributions. And that will serve you very well if you go on to study electromagnetism in more advanced context and more advanced courses. So I'll go ahead and I'll leave it at that for today. I'll post a couple of problems that have to do with finding electrical potentials, and then I think after this we're ready to move on to electric current and electric circuits, and we'll spend pretty much the rest of the semester doing that. So keep an eye out for the homework for Chapter 23, and I'll talk to you next week.